Time to raise tuition. Yeah, like right in the middle of the 8 a.m. Or not in the middle, but like about 20 minutes left in the 8 a.m. lectures. But no, it's back up and running, so hopefully we're all good. You guys are alive. Made it. I think that means almost everybody is back, except some other people have to go away. So it'll be a fun end of the semester month here. So that's it, right? You guys see that? We only got about a month left. Man, I gotta cram all the chemistry as fast as I can, no breaks, double labs. We got lab on Tuesdays now also. I don't care what other classes you guys have, right? For some of you guys, that might be good. No, I'm just kidding, right? Of course that'll be done. All right, but we had finished discussing one important idea here, and it is a key idea. The key idea is, remember, or what I try and get you guys to do, or what I want you guys to start doing, is just looking at what in the world is actually going on, right? What is happening? What do we see? What are some of these trends? What are some of the patterns? What are some of all these things that are in there, right? And where we had ended is with this discussion of do we see any structural rearrangement, right? And if we see a structural rearrangement, then we know that there has to be a carbocation that's formed. And if we know that there's a carbocation that's formed, then that's something we have to pay attention to, and we have to take care of whether it's a racemic mixture or not, and if there's a strong acid, that gives us a clue, like all these kind of things, right? But what we've dealt with so far is pretty much every time we go through some kind of SN1, or every time we go through an addition reaction, right? Really the only addition reactions we've dealt with have had carbocation intermediates. So now we need to step away from that, right? So what we're going to do is a couple of non-carbocation intermediates. And that should be good. Because if you don't have a carbocation intermediate, guess what you don't have to worry about? Shifts and rearrangements. Now, it can still form, in some cases, we can still form racemic mixtures, okay? And we'll kind of talk about that when we get there, okay? So, was that like a team thing that everyone's doing? Is that what it is? Yeah. Did you spend your own money to buy that?
I did.
I was gonna be so impressed if you said you made it, because I was gonna request one then, but that's all right too. All right. So that's the kind of idea that we're about to get into here, right? How do we avoid going through a carbocation intermediate? Okay, that's what it is. Cool. So where we had, or what we had finished with, is kind of this idea here, right? So the question I had asked is, what do we know about mercury, right? Now mercury is a transition metal. It's a cation, okay? It is going to act like a Lewis acid. Now, whenever you guys see a transition metal in organic chemistry, it's probably a safe bet to say that it's going to act like a Lewis acid, okay? Now, let me ask you guys a question. How do acids act? Like acids, got it? Now, how does a Lewis acid act? Accepts electrons, got it? A Lewis acid is an electron acceptor, okay? Lewis acid is an electron acceptor, okay? Well, where's it going to accept electrons from? Probably the double bond, right? The only functional group we have, right? But it's going to accept the electrons from the pi bond there, right? The double bond. Now, let me walk through a line of thought, okay? Don't write this down unless you need a, but let me speak first, then you guys can take your notes, okay? So if I'm accepting electrons from my pi bond, right? That's what we might be imagining, right? But what does this flow of electrons represent? Okay, this represents what? That we would create something like this, right? You guys with me? What's the problem with this though? If I follow this set of arrows, I would...
Or not a positive, but we still have a charge on something which makes an electron.
That's something to pay. Doesn't necessarily mean it's wrong. It's just something we have to, hey, should there be a charge there, right? That's important. Always assess where your charges are and what they mean. But if I draw that arrow, what did I leave off? That I want you guys to start to pay attention to.
The charge on the carbon.
What do you mean?
There's a vacant spot on the carbon.
Yeah.
It's a double bond.
Right? I took away, I used this pi bond to make a sigma bond, so what do I have to leave behind then?
Carbocation.
A carbocation, right? But what did I say about this mechanism? So is that a proper step for this? No. Okay? Now there's something else about mercury that you guys know, but that you guys aren't thinking about. Okay? I lied to you guys when I said that I couldn't read your guys' minds. Complete lie. I know exactly what you guys are thinking. Okay? Always. No, I'm just kidding. Right? Yeah, okay, what do I know about mercury? Right, that I'm not seeing. Okay. Where is mercury on the periodic table? Where specifically? All the way in our 6d row of d orbitals, right? Almost at the end, right? So what? We have our 6d orbitals. Now you guys know what a d orbital is, right? It's just a mathematical representation of the probability of an electron. So yep, Dr. H got that. Okay? Let me ask you guys a simpler question. 1s, 2s, 3s, 4s, 5s, 6s, right? Those are all s orbitals. What changes as I go from 1 to 2 to 3 to 4 to 5? True. Maybe with an asterisk. Okay. What atom is 1s? Hydrogen. What's 2s? Lithium. What's 3s? What changes as we go from hydrogen to lithium to sodium to potassium to rubidium to or cesium, whatever it is? What changes? The radius changes. Got it? Okay. So 1s, 2s, 3s. What changes as we go between those? What's the radius of measure of? The size of what? Nope.
The radius of the atom.
What's the radius of an atom? From the nucleus to what? The outermost electron. Got it? Where is the outermost electron? Well, it's in the biggest orbital shell. Got it? So as we increase our principal quantum number, 1, 2, 3, 4, 5, 6, I don't care what orbital we're dealing with, S, P, D, or F, right? As we increase our principal quantum number, the orbitals get bigger. So is a 6d orbital a pretty big orbital? Yes, it is. Okay? Is it bigger than a carbon atom? You bet. Okay? So Mercury is a big atom. Now, you guys already knew that also, right? Because we've been dealing with iodine and we talked about dispersing charges and squishiness and polarizing, right? All those ideas there, right? Yes? Okay? So the same idea is going on for Mercury. It's kind of a squishy big atom, okay? So what does that mean? That means that what's going to happen is that Mercury is going to sit directly in between the two carbons that are involved in the pi bond. And it's going to form a bond with both of those carbons. Okay? So here's what happens. That's impressive. For my next trick. Oh, there it is. Okay. So what's going to happen here is actually something that looks a little bit more like this. So here's our mercury. Okay. Try that one more time. Here's our mercury. Okay. Both of these carbons are going to start to form a bond with that mercury. So it's going to take the pi bond, okay? It's going to take the pi bond and start to form a bond between both of those carbons and the mercury. Hang on, I'll still, right? Don't draw this yet, but if you guys want to take notes, right? Because I'll show you the arrows in just a second. But you guys see what's going on here? Basically, this mercury is kind of lowering itself on top of that pi bond. And it's starting to form a bond with both of those carbons. So what size ring am I going to make? Well, there's 3 things in a ring, right? So it'd be a 3-membered ring. Do you guys start to see the problem that's going to happen here? Yeah, exactly, right? So that's going to be the important part, okay? So how do we represent this with arrows? We represent it with arrows the best we can. Let me show you guys what we typically see. Okay? What we typically see is pi bond reaches out, okay? And mercury kind of reaches down. So we see this kind of very weird setup, okay? Usually we don't see arrows like this kind of pointing back at each other, right? Got it? So we're making a bond with both of the carbons from the pi bond there, okay? I'm going to come back and add in a couple of details here and there. So leave a little bit of space.
Is the mercury from the arrow pointing at a specific carbon or just the pi bond?
Well, it's making a bond with one or the other, right? All we're saying is one, the pi bond's making a bond, the mercury is making a bond to the other carbon, right? And so what we end up doing here is basically making something that looks like, there it is, this, okay? Oops. Okay. All right. Now, as soon as you guys see any 3-membered ring, your first thought should be, there is ring strength, okay? And guess what there is here? Ring strength, got it? The mercury, not so much, right? It's a big atom, it can kind of accommodate these kind of weird angles, okay? But definitely from the carbons there. And so the carbons are going to do, or the mercury is going to start to do a sumo dance. Okay? So you guys know the stereotypical sumo mechanism, right? They go out into the ring and they throw the salt, right? Bless the ring. And then they get into their fighting position, right? I hate this part. I know. I gotta make space for my best sumo dance, right? And so then what do? Right? And they do this, right? And then they do this. Okay? So now if you imagine me making an ass of myself, that's the mechanism. Right? So if I'm the mercury atom, right? If I'm the mercury atom and each of my legs is my bond, okay? What's happening in here is basically they're doing this sumo thing where they're pulling from one side to the other, okay? To relieve that ring strain partially. Got it? So what are the consequences of this? So let's try and draw this out as best we can. I'm amazing at this. I almost did it twice. All right, so I'm just going to take this. There was my Gen Chem notes. Could you guys draw the Lewis structures for those?
Oh, yeah.
Oh, yeah. Yeah. That's amateur hour, right? So I'm just going to I'm just going to zoom in on this for a second here, just to make things a little bit easier, okay? So let's assume that we have this. What did I have? Red and black, right? Okay. So we're going to pull the mercury to either side. We're going to start to stretch that bond. Got it? So let's stretch to each side and see what happens. So if I stretch here, I weaken that bond. Okay? Do I completely break that bond? No, I do not. All I'm doing is what? Just stretching it a bit. I do weaken the bond, but I don't break it. And that's important. You guys with me on this? So I'm just pulling to one side. Okay? Then let's pull to the other side. Oh. Cool. All right, let's try that one more time here. So if I pull to the other side, right, I'm just going to end up drawing the same thing. Man, technology really helped me out today. That's my own dumb fault. All right. I hate touchscreen stuff, I really do. Well, let me get my greasy fingers and fingerprint everything. Ooh. You guys need to know my opinion on touchscreens, right? Right, so I pull to the other side. Am I weakening that red bond? Yes. Am I breaking it? No. Okay, no, I'm not. Now, which one of these is happening? The answer is both, but one of these is going to be a little bit more favored than the other. So here's the thought. I am weakening one of these red or these black bonds. Let's say I completely break my black bond, right? I completely break it. What gets left behind if I completely break this bond? A carbocation. Okay? Am I breaking that bond, though? No. Am I pulling electrons away from that carbon, though? Yes. So how is that carbon feeling?
Partially.
Pretty darn partially positive. Got it? If this was a carbocation, what would we have to do? We'd have to deal with stabilization and shifting and all that kind of stuff. Okay? Will we form a full carbocation? No. But do we form a partial cation? Yes. How do we stabilize a full cation? Well, you put it on the most substituted carbon. You guys good? How do we stabilize a partial cation? You put it on the most, you guys get the idea I'm saying? You stabilize a partial the same way you stabilize a full cation. So when you're going through and doing this mechanism, when you do your sumo dance, okay, you put your partial charge on the most substituted carbon. Good?
What if they're equally substituted?
Then you put on both of them. Okay, so I will explicitly put my partial positives there. Okay? Everyone with me? Nothing too unusual so far, right? We have this three-membered intermediate. Well, we have this ring strain that we've dealt with before, right? Instead of dealing with a full carbocation, we just deal with a partial. Got it? Now we'll have a nucleophile that comes in, okay? And what we're going to do in this case is, let's do yellow. what's gonna happen in this case is some water is gonna come in. And do this, okay? The incoming nucleophile hits the most substituted carbon and pops that ring open, okay? You guys with me? So at the end of this, right? Remember what we'd be showing here is the same thing, right? We hit the best stabilized partial positive, right, and pop that open. And what we have at the end of this, well, let me be careful here. Oops, that was in green, apologies. Okay. And then what do you guys think happens next? Well, we probably have more water around, right? So the water can come in and clean that up. And after this initial first step, you're left with this, okay?
How does the positive charge on the mercury still stay one positive?
Yep, I'll come back to that in just a second. Okay, everyone with me still? Now's the fun part of the mechanism. So this is part one. Part two is I'm going to take this, okay, and we're going to have to learn, this is going to be a pretty complex mechanism, so leave yourself a little bit of space here, okay? So part two of this reaction is we throw in something called NADH4, sodium borohydride, okay? Now, sodium borohydride is a powerful reducing agent, not the strongest, but a pretty darn good reducing agent. Okay? Now, we haven't talked about this yet, but when we talk about reducing agents and oxidizing agents in organic chemistry, we really are just kind of saying, hey, does it add or remove bonds to hydrogen? Does it add or remove bonds to oxygen? So what we're going to end up doing is taking one of the hydrogens on sodium borohydride and swapping it for the mercury. Okay? The sodium borohydride is going to come in, kick off the mercury, this kind of stuff. Amazing. Okay, you guys ready for this mechanism here? I'll show you guys what it is. It's going to be your guys' favorite mechanism, I promise. It's magic. Okay? Magic happens, and we end up with this. So what do I mean by magic? We don't know. We really don't know what the mechanism is. We have good ideas about it. Okay? We have good ideas about it, but we really don't know 100% what that mechanism is. What we do know is that if we mix these things together, we get rid of the mercury, we end up with an alcohol there, okay? And life goes on. There's theories about whether it's through a radical or whether it's through some kind of other substitution or elimination, this kind of stuff, but we just really don't know. The first part of this mechanism we know, and we're going to see other examples of it. The second part of this mechanism we just don't know. So here's where the tricky part comes in for you guys. I will expect you guys to know the first part, and I'll show you the other examples where it comes in. But I will never ask you guys to show me the reduction part of this mechanism. Okay? So sodium borohydride does magic, and we end up with our alcohol there. Got it? We do end up scrambling this, so we do end up having a racemic mixture. Okay? Guys with me on this one? Or you're like, hey, wait a minute. How could we have a racemic mixture if we don't form a cation? Right? Is that what you guys were thinking? You're like, no, it's getting hot in the room. That's what I was thinking. Was I right? Whose mind did I read? Must be losing my touch. You guys with me on this? So let's take all these ideas and summarize it together, okay? We'll give this a name, and then we'll go through the importance of it. So here's how you guys summon this reaction, okay? What we do is typically see something called mercury 2 acetate, okay, in water. And step 2 is the sodium borohydride, okay? Now, what in the world is Hagoac there? Okay. So you've got a mercury atom, and in some way, and I'm lying to you guys just so you know, okay? It is bound to an acetate. So what do we mean? That's what acetate is. This is our OAC, okay? You typically see it OAC minus. So we got some negative things bound to a mercury, okay? Obvious questions are, is it always acetate? No, okay? Does it matter if it's acetate? Sort of. And we'll see why a little bit later, okay? Do I need to know what acetate is? No. Okay. I'm just telling you what the word salad means. When you guys see this, what I do expect you to know is, I identify mercury. It is a transition metal. It has a 2+ charge to it. Whenever I see transition metals with charges, I will typically associate them with Lewis acids. If you have a Lewis acid, they're going to be used in the first step, just like every other acid. Got it? The only difference is, we're not looking for hydrogens, we're just looking for electrons, okay? Everybody with me on this? If Lewis acid, look for negatives. Make them act first. Good? Okay. If I do this reaction, here's my product. Okay. Don't forget it is racemic. All right, so we have the R and the S version of this that gets made. So we have Markovnikov addition of an alcohol with no carbocation intermediate. No rearrangements, no shifts, none of that noise. Got it? Cool. So this is called an oxymercuration. And since it's a 2-part, the next part is the demercuration. So oxymercuration demarcuration. This works from what I call the Sumo Mechanism there. There's going to be two others that we learn with it. Actually, there's going to be, well, yeah, we'll say two. But there'll be a whole part of the chapter where we deal with the Sumo Mechanism, okay? So, if you guys, or I don't know if I've explicitly said it to you guys or not, I am not going to make you guys know every mechanism that's in the book, okay? For a couple of reasons. One, it's because I don't like you guys, right? Two, is you guys are not chemists, okay? So, we don't need to know everything yet. And if you guys go off to grad school in biochemistry or something, you'll get slammed with the stuff there, right? What I will make you guys know are mechanisms that we will see repeated in other mechanisms that we learn later on, okay? This is why I bothered to teach you guys SN1, SN2, E1, and E2. Because we see these steps over and over and over and over again in other mechanisms, right? SN1 and SN2, E1, and E2 are these kind of foundational mechanistic steps. We're going to add things before and after them, okay? This Sumo type mechanism we're going to see with the chemistry of epoxides, right? And so part of chapter 12, I believe is what it is, deals with epoxides. And they all work off of this Sumo idea here. In fact, any three-membered ring is going to work off of this idea, except for when they don't, okay? But don't worry about that. You guys with me on this? So I will expect you guys to know that Sumo step, but obviously you guys don't know the magic step, so how could I ask a question about that? I can't, right? But we will know the other two reactions which we're about to learn. You guys will be able to do the full mechanisms for those, but they're based off of this idea here. Got it? Why is this reaction useful?
Because it deals with kind of like a rearrangement, but not forming a carbocation. Is that like safe to say?
There are no rearrangements. That's the whole point.
Right.
It is Markovnikov addition without a carbocation intermediate. If you have to avoid a carbocation intermediate, this is the way to go. Otherwise, you would not be able to isolate that, right? If you just do the acid-catalyzed hydration, you would see rearrangements and shifts, right? Can't do that. You have to do this method here. Good? All right. More, Dr. H. We demand more. All right. Now we want to make this. So we want to do an addition. We want to add it to the less substituted side. Well, we can know some basics already. If I'm going to add my alcohol to the less substituted side, guess what intermediate can't be formed? A carbocation. You guys got it? So again, we're going to avoid our buddy carbocation. In fact, that's usually the name of the game. Whenever you guys are actually doing synthesis in the lab and stuff like that, we try to avoid carbocations as much as we can. Okay? Because they cause problems, rearrangements and shifts, and they're slow, and a bunch of side reactions happen. Right? So we have to avoid it. Here's how we're going to avoid it. We're going to throw in, let's see here, this. Okay. Okay. So what in the world is this word salad? BH3THF. Okay. There's my good old buddy BH3. Nothing unusual about that. Here's what THF is. Tetrahydrofuran, a 5-membered ring with an oxygen in the ring. For those of you guys who've kind of wandered around the realm of biochemistry, the furan might be a term you guys have heard before. You guys have heard of Furanoses and Purinosis, right? Your cyclical form of your sugars, yes? No? No. Good. And you guys don't know if I'm right or wrong. I could be making crap up. He said ose, it sounds scientific. Okay. No, that's what it is. When you guys go through biochem, you'll learn about the cyclical form of your sugars. A furanose or a furan ring is when you have a 5-membered ring and oxygen's in there. And a pyran or a pyranose is a 6-membered ring with an oxygen as one of the parts of the ring. Okay, and you'll just talk about the equilibrium, about how sugars exist and their cyclical versus their linear form is what it is. Okay. Oh, sick to my stomach. Biochem. Me and biochem and I just a little bit too much memorization for me. Right? I'm not that smart. So here we have this. Okay, so THF. It's a very common solvent in organic chemistry. So you guys will see THF as a solvent. Okay. Now THF has that oxygen there. That oxygen has lone pairs. Those lone pairs are going to act like a donor. Okay, so they are Lewis bases. And what happens is if I put these two together, okay, we make a Lewis acid base act, where we have something that looks like this. Okay. You're like, well, why in the world would it do that? And all this kind of stuff. BH3 is just a fantastic Lewis acid. Okay. And THF is set up in such a way that those oxygen is pretty easy for it to donate its lone pairs. Who cares, right? That's not important for you guys to know. What is important for you guys to know is that this is a gas at room temperature. Kind of hard to use. Okay? So the way they make this is they make BH3 and they bubble it through some THF. And when you do that, you make this. And this you can put in a bottle. Okay? And if you put that in a bottle, it's now in its liquid form. You can add it to your reaction go, student happy, make alcohol. Okay? That's the name of the game. Get things out of the gas form and put it into the liquid form so we can actually do real science with it, right? Or maybe I should be careful. I don't mean real science. I mean easier science to do, right? Dealing with gases and all this kind of stuff, pretty difficult. You gotta use balloons and things and ugh. Okay? So the point is, we can put that in a jar and sell it. That's what it is. So if you see this, the THF doesn't really do anything. This is the thing that's doing the work, the BH3. Okay? You might see this written instead of BH3 THF as B2H6. Okay? B2H6 is just the dimeric form of BH3. Okay? Now let me rock everyone's world for a second and draw you guys the Lewis structure of BH3. Yeah! Woo! Get crazy. So this is one of these classic examples in grad school. This is where they typically start with. What's cool about this compound is that you see that hydrogen actually has what? 2 bonds to it. What I've been telling you guys all along. Only one. Okay? As promised, I just lie to your faces. Okay? Now, in reality, this isn't really 2 bonds to a hydrogen. It's what they call a 3-center 2-electron bond, right? So you can think of that bond kind of hopping back and forth. So it's a fairly weak bond in between there, but it does form, right? You guys can see it. That's how it actually looks if you guys manage to get the structure of that. Who cares, right? What's the difference between this and this? Nothing. So if you see either one of those, it's going to behave the same way. Got it? Which one should you guys put in the exam? I don't care. Just tell me that you're using the boron, okay? BH3, THF, or B2H6. I don't care. Got it? Fair enough? All right. Down here at the bottom, we got NaOH and H2O2, and sometimes you'll see H2O in here, but that's kind of an understood, okay? Water's around whenever you have peroxide and sodium hydroxide and all that kind of stuff, okay? Now the mechanism for this, it's in the book somewhere here. Let's see if I can find it real quick and kill some time. Just throwing for content here. There it is, page 364. Okay, so page 364.
Which section is that in?
8 point something. Is that helpful? No, 8.7. There it is. Yeah, 8.7. Okay. Now, do I expect you guys to know that mechanism? Nope. Why? Because you'll only see that mechanism for this particular reaction. Okay. Here is what you guys are thinking, or if you're not thinking it right now, you'll think it, Wednesday before the exam. Okay. You'll say, well, we don't have to know the mechanism. It must not be an important reaction. Okay, this is one of the most important reactions because this is the only way that we have of adding an alcohol to the less substituted side. Okay, an alcohol to the less substituted side. We don't know any other reactions to do that yet. And even once we do, this will still be one of the preferred methods of doing it. Okay. We used to do this exact reaction in lab, okay, but I changed it for reasons, okay, good reasons. But this is a classic example. If you go into any organic synthesis lab in any of the universities, you'll see bottles of BH3 THF sitting on the shelf. This is a very common reagent, a very common reaction, a very useful reaction. It's clean, it's selective, right? It's going to go after pi bonds. Extremely useful reaction. Because we add an alcohol to the less substituted side. There's no other reaction that we know how to do that yet. Got it? Do you guys know how to do a lot of reactions with alcohols? You should, right? You could substitute them, you could eliminate them, right? Now we know how to add them to the less substituted side. Good? Everyone understand me? I'm making it very clear what's important to know about this reaction. Is it going to show up on the next exam? Oh yeah, is it going to show up on the exam after that? And the first exam of OChem 2? And the second exam? Literally, this is one of the only reactions we're going to learn about how to add things to the less substituted side for an alcohol, okay? So it's important. We can do a lot with alcohols. Now we're going to learn some other methods along the way and here and there, but this is one of the best methods that we have, okay? By the way, speaking of OChem 2, I think I told half of you guys, and I forgot the other half, and I don't remember which half was what, but so there was a change in the scheduling. So we have to do OChem 2, I think it's at 2:30 now, next semester. So, it's really bad for you guys. You know why? 'Cause I'm a morning person. So when it gets to the afternoon, guess what happens to me? Grumpy, okay? And guess who gets the brunt of all that grunt? You guys do, okay? Sit here and just right? Ask you guys really hard questions, make you guys think a lot, right? Sounds terrible. Don't sign up for it. I'm kidding, right? But anyway, 2:30 is when this change of schedule there. So just, I think what registration opens on Monday for you guys, is that what it is? For some of you guys? All right, so just keep that in mind. If you guys have already made your schedule, you might have to go through and kind of change some things there. Good? Okay. Hopefully good. Anyway, BH3, THF, add things less substituted side. And I can tell what you guys are thinking. We want more, Dr. H. Give us more. But first, I've done enough talking. So I want you guys to think. Ready? Go ahead. Make that form. I'll go and let you know. I'm going to trick you. I like what you're thinking with that, but don't make things up like that. Mm-hmm. No ideas,
No, I did, I just noticed it.
Oh, okay, sorry, I misunderstood. Don't make things up. That's me saying don't get creative, right? Tricked Freddy. Give you a hint, you can't do it in one step. I have at least, right now, it's gonna take us 3 steps. I'm not talking about 3 mechanism steps, I'm talking about 3 different reactions to get through. We can take more of it if you guys want. Like, no, 3's good. Before you take the journey of even 3 steps, what's the most important thing to do? Observe, think, analyze, right? So what do we need to observe, think, and analyze here? Well, what do we need to accomplish on this reaction here, or this synthesis?
Rearrangement. Rearrangement.
Rearrangement of what?
The pi bond is gone.
So addition, right? An addition reaction, right? We know we have to get rid of our pi bond through an addition reaction. The bromine is added to one of the carbons that was in the pi bond, right? So no structural rearrangement. But we also know there can't have been a cation that formed. How do we know that? Otherwise, if there was a cation, it would have shifted next door to that tertiary carbon. You guys with me on this? So, what's the only reaction we know so far that we can add something that doesn't shift it? Or oxymercuration demercuration. So follow along with me, okay? So the first step here, we got to do our oxymercuration demercuration. And we're going to make that double bond into an alcohol. Now we have an alcohol where our bromine's supposed to be. Got it? So how can we swap an alcohol for a bromine? What type of reaction do we need to do? That is a substitution. What's the problem with doing a substitution with an alcohol? It's a terrible leaving group. So we need to make our alcohol into a good leaving group and then do a substitution. You guys got the 3 steps? Addition without rearrangement, turn the alcohol into a good leaving group, and then do your substitution. And then cry. 4 steps. That one can come first though, I don't care. Why do I have to go through a tosylate to do this? What's the only other way we know of turning an alcohol into a good leaving group?
Making it into water.
Hmm?
Making it into water.
Make it into water by adding what?
Strong acid.
Strong acid. But if we add strong acid, what do we form? Carbocations. If we do carbocations, what happens? Rearrangement, shifts, right? So you get the whole point behind this exercise? do everything we've been doing, but avoiding carbocations. Got it? So avoid using strong acids. So now we got an oats, right? How do we turn the oats into what we want? What type of reaction do we have to set up here? An SN2. How do you know it has to be an SN2? Well, we know it has to do a substitution, right? And we have to avoid forming what? Carbocation. So what's the only substitution that we know that avoids a carbocation? SN2. What do we need to do an SN2? What are the conditions? A strong nucleophile. Now, what are we trying to substitute it in? A bromine. Is Br by itself a strong nucleophile? No. Hang on, here's what I mean. Right, can we just throw in bromine by itself? Is that a strong nucleophile? No. But how can we make bromine a good nucleophile? What makes a good nucleophile? Not just a negative charge, but a squishy negative charge, right? So how can we make bromine have a squishy negative charge? Well, that's easy. We just throw in some what? Br minus. Got it? Is that a decent nucleophile? Actually, yeah. Is it a great nucleophile? Right? Yeah. Now, obviously, we can't just throw in Br minus because that can't exist. So how can we balance out that minus charge? No. No. We don't want to make it a strong acid, right? So we just throw in some sodium bromide. Does that seem fair? Is sodium going to participate in this reaction? Nope. Anytime you see a sodium, whatever it's bound to, right, has a negative charge. So there you go. This seems a fair way of doing this. And we're going to start to see some of these questions pop up here and there. Having you guys start to string 2, 3, 4 steps together. 5. But not 6. Maybe 7 then. No, I'm just gonna ignore my stupidity, I'm sorry. Right? Well, I'm going to start to think how we can use these reactions sequentially to build something. I believe it's chapter 10 that deals with this. The synthesis chapter, I forget which one it is. Don't worry, I brought my book. Sorry, chapter 11. Okay, so chapter 11 is where you start to see these ideas come in. The synthesis chapter. Okay.
Should we draw the arrows for all this, or do we just?
Draw the mechanisms?
Yeah.
Yeah, you could draw the mechanisms for these.
How do we draw the mechanism with the mercury salad on top?
Yeah, we don't do that. I'll never ask you to draw that mechanism.
Okay.
But you guys could do the mechanism for the other ones. I think we did them all in class, didn't we? Did we?
And we did the.
Did I show you guys the tosylate one in class? No, I can't remember.
Yeah.
I did, yes? Okay, cool. I mean, it's just an SN2 reaction, right? So, but, yeah.
So we wouldn't, will we have to do up the first part of the mercury?
No, that one no, but you guys should be able to do the other ones in here, yeah.
Okay.
Yeah. Any of these ones that I'm, as much as I joke with you guys, I'm never gonna be like, haha, I told them not to know this, and then I'm gonna give them an exam, right? I'm never gonna ask you guys to do a mechanism that I tell you explicitly, hey, you guys don't need to know this one. It doesn't mean it wouldn't be good to go look at it, right? I hate having to tell you guys not to know a mechanism. You know why? Because as soon as I do that, what are you guys gonna do? Memorize it, right? As soon as you memorize something, what's gonna happen? You're gonna forget it in 2 weeks. Okay? If you forget it in 2 weeks, what's gonna happen? Sad noises, right? You're gonna look at an exam and go, oh, right? So be careful. It's always good to understand, right? That's why I showed you guys mechanism. Once you understand something, you're not gonna forget it. unless you try really hard, right? I believe in you guys. Okay? So, we got that. Let me ask you guys another question. Could you guys do this? That's almost our time also there, so it might be a good, let's say this is a good homework assignment. But before we go, right, always the first and the most important thing to do is to gather as much information as you can, right? Assess what's going on, think about what it means, okay? So here, similar to what we saw last time, we know we have to do an addition, where we have that bromine at the end, was part of the pi bond to begin with, but we also see that it was added to the less substituted side. Got it? So again, we could make the statement that we know we have to avoid carbocations because we can't go through any mechanisms that generate primary carbocations. Got it? And we only know one reaction so far that can add things to the less substituted side. Make sense? So I think those are all the puzzle pieces we need, and I think you guys can get it from there. But we'll pick that up on Monday. I will post for you guys I'm going to teach you guys one new thing for the exam on Monday, and I'll post all the sections for you guys today so you guys can look through that stuff. Okay?